All right, so here's a neuron. And upstream, okay, think about the way water flows in a creek or a stream. So we have several upstream neurons. And the question is, does the downstream neuron fire? Does the blue neuron fire? Okay, it's resting at -70. What does it have to reach to fire? -55. So what if this neuron sends a signal of +5? What does that do to the -70? -65? Would the blue neuron fire? No, it didn't reach threshold. But what if simultaneously these three neurons sent a signal of +5? Zap! What's that do to the -70? Becomes -55. And it fires. That's spatial summation. Space, place. So spatial summation is the summation over different places in space. So it's spatial because we had three upstream neurons. They're sending their signal in different places. All right, another example. So we're resting at -70. And this neuron goes bang, bang, bang. In rapid succession. What's that take us to? -55. So it fires. Okay, what kind of summation was that? They all came in the same place. So it's not spatial. It's temporal, meaning over time. Summation over time. Now they have to come in rapid succession. If they came in bang, bang, nothing would happen. So if you look at that one graphically, so the first time this neuron fires, we go up 5 points. Before it goes down, that neuron's got to fire again. You take it up another 5 points. And before it goes down, that neuron's got to fire again and take it up another 5 points. If it wasn't bang, 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 if it was bang, 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 well, then after the first one fired, it would just go back to rest. So those signals must come in rapid succession. Now, in the spatial summation, because they all came in at the same time, we just went straight to threshold. Let's combine the two. We'll change to green. So we're resting at -70. So this neuron fires, and this neuron fires simultaneously. So that's spatial, but then this one fires a second time. So it's bang, bang. So we have temporal and spatial. Guys, this is what's going on in your brain at a rate of billions of times per second. As you feel this way or that way, I love her. I hate her. I'm happy. I need to throw the ball. It's time to get out of bed. In the simplest little thing, Poppy's hungry. You know, billions and billions of these are happening. And we've got one blue downstream neuron and 5 purple upstream neurons. Well, attach 5 upstream neurons to this one, and this one, and that one. And attach 5 upstream neurons to each of those. You see, this is what we figured out, kind of, sort of, how to do with vacuum tubes. And Joanna might have seen a vacuum tube. I don't think, not calling you old, but the rest of you are way too young to have ever seen a vacuum tube. But, you know, TVs and things, they used to be huge because we didn't have transistors. And when we created transistors, everything got smaller and faster. I remember seeing a transistor when I was 8 or 9 years old, and it looked like a granddaddy long-legged spider or whatever those things are called, big old thing. And my dad said, son, one day they'll be able to put 10,000 of these on the head of a pin. I'm hungry. Can we go eat? And how many millions of them now can they put on the head of a pin? This is what makes computers and everything possible. The computer in your watch. Guys, this calculator is more powerful than the computer that took us to the moon, landed us, and brought us home. That's how far we've come in trying to mimic this with computers. I remember the first computer. It might fit in this room. Guess what it could do? It could count to 10. That's it. That's all it could do. It could count to 10. How far we've come. And now imagine how we're pushing this as we move toward artificial intelligence. As far as we've come with processors and processing, the fastest, most powerful computer on the earth is stupid compared to a fruit fly. A fruit fly. You might call them house flies. You see one, you swat it. Smartest, fastest computer on the planet is dumb compared to a fruit fly. But we're trying to mimic what happens in the human brain. All right, so that is action potentials. How does a signal get through a neuron? What's next? Synaptic potential. So you know that the synapse is this space between the two cells. And as I've said before, it can be neuron, neuron, neuron muscle, neuron gland. It's still a synapse. And we know the chemicals that move the signal across the synapse are called what, Pablo? Neurotransmitters. And Jocelyn, we know the most common neurotransmitter in the body is acetylcholine. Once again, you got to pull it out of your brain or flip back in your notes. So synaptic potential is how the neurotransmitter works. Now, there are many neurotransmitters in the body. Acetylcholine, because it's the most common, and I mean, it's the most common in the CNS, the PNS, it's the most common. Because it's the most common, it's the acetylcholine model that it's critical that you master it. And it's not that difficult, but it's critical that you understand it. And then that makes understanding all the others easier. The reason that I picked serotonin as our other neurotransmitter to talk about is because serotonin is one of the, oh God, please. 3 days, guys, 3 days. Serotonin is one of the feel-good hormones. Extra serotonin, you're stoned. That's what ecstasy does to you. Not enough serotonin, you're depressed. That's called clinical depression. There are other feel-good hormones, norepinephrine, or rather neurotransmitters, norepinephrine, dopamine. We'll talk about norepinephrine next semester. Right now we're going to talk about acetylcholine and then serotonin. All right, give yourselves a clean sheet of paper turned sideways and a second sheet of paper to go with the small board. Okay, so once in, don't draw this. Again, we're looking at what happens right there. We're going to have a huge picture of that. Okay? So that's the axon terminus. Down here we have the dendrite or other cell. Because remember, it doesn't have to be nerve. It can be nerve muscle, nerve gland. In the axon terminus, we have vesicles. Let's come over here for a second. And the vesicles contain the neurotransmitter. So in this case, acetylcholine. Over here on the postsynaptic cell, so it's another way we could name these: pre-synaptic cell, post-synaptic cell, primary cell, secondary cell.
Board.
Thank you. First order cell, second order cell. So on our postsynaptic cell, we have receptors for acetylcholine. The acetylcholine receptor specificity is like sucrase being specific for sucrose, or an enzyme in any enzyme in substrate. So our purple things are receptors for acetylcholine. They contain sodium gate. A chemical gate. Remember, it's chemical gates that open first, do or don't get us to threshold. If we reach threshold, then voltage regulated gates open. So you can envision some type of little pore in that receptor that can open and close. There's a way to just tear it off the wall and have it be the other end. There's also an enzyme associated with that receptor. Hang on. Okay, so I added the enzyme in red associated with that receptor. The name of the enzyme is acetylcholine esterase. There's that suffix again, ase. Acetylcholine esterase will break down acetylcholine almost as fast as it binds. Break down acetylcholine almost as fast as it binds. Why break it down almost as fast as it binds? We want to prevent continuous stimulation. We don't want one upstream event to cause continuous downstream stimulation. I pick this up and I hold it forever. How do I put it down? If I want to pick it up and hold it forever, then I need continuous zing, 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 continuous action potentials coming in. So acetylcholine, break down acetylcholine almost as fast as it binds to prevent continuous stimulation. Okay, so this is just the anatomy. Now let's see how it works. The action potential reaches axon terminus. Much prettier than anything I could draw. The action potential traveling through the axon, it reaches the axon terminus. Then we get the influx of calcium. So calcium diffuses right into that axon, the very end of the axon. Now, let me just tell you up front, again, go back to plain old biology. These are vesicles. What do vesicles do? We engulf things through phagocytosis, pinocytosis, collectively endocytosis, and vesiculate them, and then vessels fuse with membranes and release their contents through exocytosis. So that's all that's going to happen right here. We're going to exocytotically release the acetylcholine. So the synaptic vesicles fuse with the presynaptic membrane. So we can sort of diagram that. Showing a couple of them fusing with the membrane. And again, it's just plain old basic biology, exocytosis. Vesicles exocytotically release acetylcholine. With one of these, erase a little bit and try to show the acetylcholine being released. So acetylcholine has filled the synapse, pardon me. Just to make sure we're all clear here, all of these blue dots in the synapse, those represent molecules of acetylcholine. So the action potential got to the end of the axon, calcium moved in, vesicles fused with membrane, exocytosis occurred, and the vesicles released their contents. In this case, acetylcholine. In a minute, it'll be serotonin. Again, this is the most common neurotransmitter, and if you understand this model, all the others are simple. So now the acetylcholine binds receptors on the postsynaptic membrane. This binding opens the chemical gates and allows the influx of sodium. So we've opened chemical gates. You should be able to finish this. If we reach threshold, the voltage regulated gates open. And the signal continues downstream. And then just so that you don't forget, we'll end it here. Acetylcholine esterase breaks down acetylcholine. Of course, I've already mentioned that on the small board. Is it so hard to sit? As you visualize this, imagine it happening where all of these upstream neurons synapse with the downstream neuron. And so does the downstream neuron fire or not? I don't know. What's the cell body do? It integrates the incoming information. One of these neurons could be sending an excitatory signal. One could be sending an inhibitory signal. So if you picture the graph, if we're at rest, an excitatory signal is a positive value and moves us toward threshold. An inhibitory signal is a negative value and moves us further away. When you go below the resting differential, that's called hyperpolarization. Remember that polarity means there is a voltage differential. How polar were we? Negative 70 millivolts. Well, now we're more like negative 8, so we're more polar. So the term hyperpolarization. All right, guys, so this is just a taste of what's happening. Billion times a second. Every tear you shed, every blink of the eye, everything in the world. While it's hard to imagine, there is a molecular basis for everything. So imagine, I don't know, why does it hurt so bad? I'm just sitting down. imagine having some explanation like this to explain feelings or emotions. As a young man approached the girl, he was going to ask her on a date. He was very nervous. The closer he got to her, the more nervous he became. Why? Well, because calcium went in and zinc came out and sodium went in and potassium came out. I mean, I can imagine explaining emotions at that level, but are you willing to say we'll never be able to do that? I'm not willing to say we'll never be able to do that. You know, how many times have you heard that? It's stupid. Now, men were meant to fly, we'd have wings. Before we ever flew. So everything that's ever been said we couldn't do, we've done. All right, so leave this picture in front of you. Main board picture. Well, it may be in my way because I've got to pull some internet stuff up. See how it goes. Okay, so we're going to talk about serotonin next, our next neurotransmitter. It's similar to this, but remind me what happens to acetylcholine after it's released? It binds, opens the chemical gates. What happens next?
Broken down.
It's broken down. It's released, it binds, and it's broken down. Hang on to that. So I'm not getting up yet. So write these down. These feel-good hormones are and they're hormones and neurotransmitters. When a chemical like serotonin is traveling in your blood, it's acting like a hormone. When it's released at a synapse, it's acting like a neurotransmitter. So we have lots of chemicals that are both. Epinephrine is another one. All right, so you've got serotonin, you see that one, write down dopamine and norepinephrine as well. Now, again, the reason I like to talk about serotonin is because it allows us to talk about clinical depression. First of all, what is clinical depression? Well, it's a diagnosis. It's not, I was backing out of my garage and ran over the cat and I'm sad. Of course you are. But you're going to get over it. I remember when my mother died. I was sad. I still miss her every year on her birthday, which kind of makes the holiday season suck. Her birthday is New Year's Eve. But I'm a normal functioning person. I don't dwell on it. It doesn't cause me to do weird things, crazy things. I'm not just sitting around all sad 24/7, 365. So clinical depression is a specific diagnosis. Write that word down, diagnosis. When you see your provider, doctor, MD or DO, nurse practitioner, PA, your provider, and you have an issue, he or she makes a diagnosis. And there's nothing arbitrary about it. For any diagnosis, there might be a list of 12 things, and you might have to meet 8 of the 12 or 10 of the 12. And there's tens of thousands of diagnoses, like bronchitis, bronchiolitis, laceration over the left zygomatic bone, 2 centimeters or less, laceration over the left zygomatic bone, 2 to 3 centimeters, acute sinusitis, recurrent acute sinusitis, everything imaginable. Clinical depression is a diagnosis, highly specific. It's no more arbitrary than broken femur. Have a broken femur or you don't. What type of fracture is it? So again, it's not I'm sad because this happened. Of course you are. You're going to get over it. Sometimes you know the root of clinical depression. There was an event, loss of a loved one, and you don't get over it. Like I have a friend who lost her sister, and it's been years, and she's still affected almost every single day. That's clinical depression. Other times there's not a specific event that you would say that was the catalyst. You might be at your provider's office for some type of annual visit. And they, how have you been? How are you doing, Jocelyn? And you say, dang, come to think of it, I felt kind of crappy for the last 6 months. And the provider says, really? Anything you can put your finger on? How are the kids? Oh, kids are great. They all got scholarships to Harvard. How's the job? Oh, I just got a raise. I make $10 million a year. You know, anything the provider asks you, it's through the roof. You can't put your finger on it. That could be clinical depression. But again, it is a highly specific diagnosis, just like sinusitis or bronchitis. There are codes for these diagnoses. The coding system, we were up to ICD-9-CM, and people kept presenting in the ED with something that we didn't have a code for. ICD-9-CM had perhaps, and I don't really remember, so I'm going to say 16,000 codes. And you have people called coders that assign those codes. You can actually get a certificate here and be a coder. It's kind of a cool job because you can do it from home. The coders learn the codes that they use frequently. So if you're a coder and you work for a group of orthopedic surgeons, you're going to know those codes. But if you then you filled in as a temp for a GI doctor, you'd have to look all the codes up. You wouldn't know them. It's like the checker at King Soopers. They're checking you out, you know, green pepper, 46.53, onion, 69.70. They don't have to look that code up. They know it. But then they get something weird that they don't see a lot of, like a red Fresno pepper. Like, do you even know what this is? And you tell them it's a red Fresno pepper, and they have to find the code. But so there weren't enough codes here. So we're up to ICD-10-CM. And again, I don't remember the exact number, but something like 65,000 codes. You could Google that if you wanted to know. Now, the hole I'm going to crawl into now is for fun. Again, ICD-10 came about because people kept presenting with something that there was not a code for. So let's look at some of the craziest ICD-10-CM codes. All right, walked into a lamppost, subsequent encounter, pecked by a chicken. So that means somebody went to the emergency room in some city in the United States and they had a little cut or something. What happened? I was pecked by a chicken. They didn't have a code for it. Well, you can't do anything without a code. The code determines what your insurance company is going to pay the provider, whether or not it's surgical. If it's surgical, is it spend the night or same day? Everything is in that code. So with no code, the world stops. So look at some of these. Bitten by a pig, struck by a turtle, sucked into a jet engine, subsequent encounter. How on earth? Fecal urgency, what is that even? Swimming pool of prison as the place of occurrence. Well, if I go to prison, I want to go there. Stabbed while crocheting. Burned due to water skis on fire, subsequent encounter. ICD-10-CM was designed to have a code for everything. Hence these bizarre codes. Spacecraft collision, injuring occupant. God almighty. And you see there's a, an alphanumeric code for each of these things. If you were to look up sinusitis, you'd find dozens, if not 20, 30, 40, 50 codes for sinusitis. Again, chronic, acute, recurrent, first occurrence. Which sinus? Bilateral, just everything in the world. That, again, that's what your insurance company uses. That's how our system works. Okay, so make sure you remember all those codes I showed you. Okay, so serotonin. So with clinical depression, we think the problem is most often serotonin. Secondly, norepinephrine. Third, dopamine. But of the three, most likely serotonin. But you don't know what the problem is. Because what you do with the serotonin you release it into the synapse, just like we did acetylcholine. It binds the receptors, just like the acetylcholine did. But what happens to the acetylcholine next? It's broken down. Acetylcholine esterase breaks it down. Works a little differently with the serotonin. Serotonin is reabsorbed. Into the presynaptic neuron. So the serotonin is released, binds, and is reabsorbed. Now the problem with the serotonin, you're not going to know which one it is, but possibilities would include maybe you don't make enough serotonin. If you don't make enough, you can't release it. Maybe it binds too quickly, doesn't stay attached long enough. Maybe there's some enzyme that's breaking the serotonin down. You're not going to know, but you try, and you can look at the lecture outline, that category of drugs called selective serotonin reuptake inhibitors. What do SSRIs inhibit that I just showed you happens here? They inhibit the reabsorption. So that keeps the serotonin in the synapse longer, increasing the chance of downstream stimulation. What would an SNRI be? Norepinephrine. And an SDRI, dopamine. And most of them probably have a little overlap, as opposed to this drug just affects serotonin or just affects norepinephrine. Trying to think of some you might have heard of. Prozac, one of the very first ones. That's a SSRI. Paxil is another SSRI. Wellbutrin and Zyban are the same thing. And they're SNRIs. Now the thing with Wellbutrin and Zyban, this again is how crazy our medical industry is. Wellbutrin is used for clinical depression. Zyban has been marketed for smoking cessation. Remember, they're the same drug, but made by two different companies. Because Zyban's been marketed for smoking cessation, a lot of insurance companies won't pay for it because they won't pay to help you quit smoking. They'll pay for the lung transplant, the coronary bypass surgery and all of that, but they won't pay to help you quit the problem. So you have the exact same drug, but if the doc writes Zyban, no. Writes Wellbutrin, sure, we'll pay for that. That's the way our medical community works. Crazy, huh? All right, questions on any of this? If you're, and I know some of you do this kind of thing at home, if you're interested, there are beautiful, beautiful animations online showing both of these models, all of these models. And I mean, some of them were, written for high school, so they're, very easy to understand. I was pecked by a chicken this morning. Okay, at this point, you should be looking at your, yep, we're done, that's it. You should be looking at your exam 3 and final exam reviews. Some of you worked on them, well, hopefully all of you worked on them over the weekend, but I know some of you did because you emailed me questions.
They're from two, but they're spatial.
It'd be both,
That or it's just
temporal and spatial. So this is what I understand you to be saying. So there's our downstream neuron resting at -70, and oh God. So this neuron fires +5, and that one fires +5 simultaneously. So that part's spatial, but whereas this one fires once, this one fires twice. So we reach threshold, and this part is temporal. Is that what you were? Yeah. So it would be described as spatial and temporal. There's not another name that combines the two. So what is let me see if I can find it. One person had the question, somebody else might. Okay, so talk about letter D. How do niacin and riboflavin relate to NAD and FAD? Not the person that I already talked to about it. Anybody else? You in this room. Make NAD out of niacin, we make FAD out of riboflavin. What vitamins are niacin and riboflavin? We talked about this. I said that's why the B vitamins are considered the energy vitamins. Somebody feeling sluggish and lethargic might buy a B complex. Their physician might suggest they buy a B complex. That would have megadoses of all the B vitamins. Questions, guys? Okay, when we get upstairs, I'll unlock the door. You guys will get the cadaver out of the closet. You know where it goes, what position it goes in, all of that. You'll locate 25 pins. You'll probably be able to find most of them as yellow. You might have one or two blue ones mixed in there to get the full set of 25. When we get up there, go in through the door, turn right immediately. That area of counter right there, that's the designated nasty zone. So that's where the pins 1 through 25 in order, just to facilitate getting it done as quickly as possible. One of you will be handing me the pins, say number 6, 15, 5, and you'll hand me the pin. So then once it's pinned, the people that want to do the matching first will sit. People that want to do the identification first will remain standing. And that way we won't have everybody around the cadaver at the same time. 15 people in the lab, we'll have 7 or 8 around the cadaver, 7 or 8 doing the matching. I do my best, and I'm 9 times out of 10, I succeed with getting you this practical grade, just like I've got you every other grade, basically instantly. The part that's a little different that you have to understand is I don't go run the scantrons until I have them all. So, if you've turned in your identification and your scantron, but there's still, people working, I'm not going to go run the scantrons, because then I have to go run them again, run them again. So not until everybody's finished that I'm able to give you your grade. At the top of the identification page, you'll see something like identification score, matching score, combined score, and everything's based on 100, so that it's, that's just how we work in academia. So let's say that on your identification you made a 90, and on your matching you made an 80. So we have to simply average those numbers. So what does that come out to? 85 would be your grade. So that's what will go into D2L. Okay, anything else? Yes.
My micro teacher.
For my final, you need 3 Scantrons. Even the final that Jennifer's going to administer next week, yeah, it's got 300 questions. So you'll need 3 Scantrons. You also need 2 blue books for the essay portion. There's also an oral presentation. You'll be doing those Saturday afternoon. Be out in the field across from the college.
I am your
Well, no, oh, yeah, because I will, yeah, because surgery's Thursday. Yeah, so I will be high by then. You need 1 Scantron. 1 Scantron for exam 3, 1 Scantron for the final, 1 Scantron for today's muscle matching. Sorry. So you need 2 for the micro final?
Yeah, she said it's just over 100, that we just need like an extra 10.
Whose class is it?
Professor Moran,
Amber, she's awesome.
I like her. I've been studying to figure out how to know.
Oh, you guys know what? Not that you necessarily care, but I know some of you do. I've got some really thoughtful emails from some of you about the surgery. But the reason the weekend was so horrible and the pain is so much worse. What do you know about non-steroidal anti-inflammatories? Think aspirin therapy. People take aspirin every day to decrease blood clots. Well, before surgery, you have to eliminate all non-steroidal anti-inflammatories for a week. So as of Thursday of last week, I was no longer taking the ibuprofen. I was taking 800 milligrams every 6 hours around the clock. So that was a huge change to lose that. Anyway, that's why the pain is so much worse. I just have to suck it up, I guess. All right.